Many robotics algorithms, such as control or collision detection, can benefit from accurate and high-bandwidth link velocity in acceleration. However, numerically differentiating the encoder's signal is not a viable solution, as the noise characteristics intensify after each differentiation. We have indeed shown that we can estimate the manipulator's link variables by fusing the robot's proprioceptive measurements with inertial measurement units. We have previously shown that we can estimate the manipulator link variables, including link velocity and acceleration, by fusing IMUs with the robot motor encoders. For this, we install 1 IMU per manipulator link. The measurements are consequently fused in a nonlinear estimator with the following dynamics model. It is evident that this method is computationally cheap, easy to implement, and covers a wide range of trajectories. Note that each IMU consists of an accelerometer and a gyroscope. The extended Kalman filter leverages the fundamental principles of the Kalman filter by linearizing the system around the current state. This linearization is achieved through the utilization of Taylor series expansion, typically involving the initial terms only. Therefore, the filter performs well as long as the system nonlinearities are not severe. The state transition function is linear in the dynamics model we use to estimate link velocity and acceleration. Moreover, the measurement function is a second-order polynomial with respect to the system states, with its nonlinearities deemed of minor significance. Therefore, we use the extended Kalman filter as the nonlinear estimator for this system. Kalman filter is an optimal filter for linear systems with white Gaussian noise when the system, as well as noise information, are precisely modeled. On the other hand, the extended Kalman filter is intrinsically suboptimal. The filter performance further degrades when either the system model or the noise information is poor. We mainly focus on the imperfection in the noise covariance that is provided to the filter. One can manually tune the filter. However, this can be challenging and time-consuming. Also, it results in poor performance once a part of the system, such as sensors' properties, change with time. In this paper, we propose an adaptive extended Kalman filter that is based on maximum likelihood. More specifically, the covariance of the innovation sequence is computed based on a moving horizon of a fixed size. In this case, the corresponding covariance is exact, meaning that no approximation method is used in the calculations. Also, the covariance is recent, reflecting the system's current state. Accordingly, we can adapt the noise covariance matrices. Note that the stability of this type of adaptive filter is rarely discussed in the literature. It can be shown that an estimator is stable as long as the provided dynamics model is observable and the initial estimation error and its covariance are bounded. Finally, the noise covariance must remain bounded. With the discussed adaptation method, the latter is in question. In fact, it can be shown that the proposed covariance matrix of the innovation sequence grows with the number of iterations. Therefore, we propose 3 methods to maintain filter stability. First, the adaptation starts when the system's transient behavior is over. Second, we impose a degree of freedom to tune the adaptation rate. Finally, the adaptation stops when the condition number of the noise covariance matrices grows large. We have installed 1 IMU per manipulator link. The robot moves in an excitation trajectory. We compare our method against a state-of-the-art adaptation method based on covariance matching. This method uses the Taylor series to approximate the current noise covariance. The conventional extended Kalman filter performs relatively well, according to the results. The reason is that the filter is initially tuned well, and the noise covariance is relatively accurate. Since approximations are utilized in the covariance matching, the performance of the state-of-the-art method is not competent. On the other hand, when the horizon window is appropriately picked, the proposed method works acceptably. The reason is that the noise covariance is adapted based on the true and recent covariance of the innovation sequence.